So in part 6, we will deal with the steady state error and PID control of systems. As the name says, steady state error refers to the difference between the input and the output as the time goes to infinity. It's a measure of system accuracy. Now, if you see this graph, this is drawn with respect to output y as a function of time in x-axis. Now here we have input here. This is the input. That means this is the input we expect. Input means this is the output we expect from the system. Now actual input is output 1, output 2. There are two outputs shown here. As we can see, this output 1 is matching with the input. That means here there is no error. This output 1 is exactly same as what we expect from the system. So there is no error here. But if you see output 2, as the time goes to infinity here, the output is at this level, whereas what we want is here. So this difference is called steady state error. Means when the system reaches steady state, what is the output and how much is that output different from what we expect. That is called steady state error. Now this is that E. This E is the error. Now this steady state error depends on what is called a type number of the system. Now we have been discussing system order. System order means first order means it's a system which has derivative of order 1 and second order system has derivative of order 2 like that. Now this is a different thing. This is called type number. This type number refers to the number of poles at the origin of the S-plane. We know what is the meaning of poles. Poles can be anywhere in the S-plane. But if you have a pole, if you have one pole on the origin, that means if the pole is at 0, that is called a pole at origin. So if the system has one such pole, then we call type number 1. If there are two poles like that, then we call type number 2. Let us see some examples here. First transfer function is k over s plus 1, s square plus 6, s plus 8. If you see this transfer function, here there is one s. That means this s has got a pole at s equal to 0. So since we have only one such pole, this system has a type number of 1. But if you say the same system and see system order, it is fourth order because we have s square, again s square, so s power 4. So for this system order is 4, whereas the type number is 1. Now let us take the other system here. This system, if you see, there is a pole at plus 1 and another pole at minus 3. There is no pole here where the pole is at 0. So this system is of type number 0. In other words, if you see the transfer function and if you see there is one s, it is called type number 1. If you have s square, it is type number 2, like that. So this type number dictates how the steady state error of a system will be. We will see it later in the coming slides. To find the steady state error of any system, we use what is called a final value theorem. Maybe you know this from Laplace transformations, which you might have studied in semester 5. So this says if you have a function f of t and let t go to infinity, that means I want to know what happens to the function f of t as time goes to infinity. It is similar to saying take the Laplace of that function, multiply with s, that is sfs, and then s tends to 0. That means if you want to know what happens to the system when time goes to infinity, you have to do what? Get the Laplace transform of that function, multiply with s, and then allow this s to go to 0. It's like saying time going to infinity is similar to s going to 0 for this function. Now, why this final value theorem is important? This final value theorem is important because this can be applied only if the closed loop transfer function is stable. Now, the key word here is closed loop. So, if you have a function, take the closed loop function for the system, and if it is stable, then only you can apply this final value theorem, because it is logical. If your system is not stable, then it will keep on going dancing like this. It is not going to settle. So we don't have any value to compare and say that this is different from the input we want. Okay, so to find whether the system is stable or not, we know the procedure. Like in part 5, we discuss Routh criterion, which will help you to say whether the system is stable or not. Now, if the system is stable, then we can apply final value theorem and get the steady state error. So this is a common expression for finding steady state error. This E of infinity means the error as time goes to infinity. Is limit s tends to 0, s rs over 1 plus gs. Now this rs, gs all are coming from this system. You can refer to this figure here and go back to that formula here. Now we will apply this theorem for different type of inputs and see what type of error we are going to get. The first case is step input. As you know, if the step is unit step, then this R of s, that is Laplace of unit step, is 1 over s. So if you apply here E infinity, that is E step infinity, because we are applying a step input, is limit s tends to 0, this s. Now this R of s is 1 over s over 1 plus g of s. Now this s will get cancelled here. So you have 1 over 1 plus limit s tends to 0 g of s. This is the case of step input. Now we'll take ramp input. For ramp input, you can refer to the Laplace slides, Laplace table, what we used in part 2 and 3. That table says for ramp input, this Laplace will be 1 over s square. So if you apply this 1 over s square here, then you have this s will go with 1s here. So we have 1 over s plus sgs. Now this is if you want to write in terms of the formula directly. There is another way of doing this, that is to use what is called static error constants. To use static error constants, we are going to define three constants, namely position constant Kp, velocity constant Kv, and acceleration constant Ka. This position constant Kp is defined as limit s tends to 0 g of s. That means you have a function g of s. Just put s equal to 0 here, you will get a number, and that number is Kp. Then Kv is similar to Kp, but you are going to apply limit s tends to 0, not to Gs but s times Gs. Similarly, Ka, that acceleration constant, is given by limit s tends to 0, s square g of s. That is s square, it keeps going like this. Before we mentioned that the steady state error depends on the type number of the system. Now there may be cases in which you don't have any steady state error. There are cases in which you have error but which is finite, and there are cases in which you have infinite error. Now this table shows what type of systems, what type of type numbers will give you what type of errors for what type of inputs. So here we have inputs, step input, ramp input, parabolic input, and here we have type number, type 0, type 1, type 2. The first, this column says the formula to be used for finding steady state error. From this you can see if the input is a step input, Kp is involved. If it's a ramp input, Kb is involved, and if it's a parabolic input, it's Ka which is involved. Let's take type 0 system first. Now I have a type 0 system. Maybe you can recollect type 0 system is a system in which there is no free s in the denominator, means there is no pole at s equal to 0. So if you have type 0 system and you apply a step input to the system, this Kp is constant and the error will be 1 over 1 plus Kp. Now if you take the same input, step input, but apply to type 1 system, static error constant is Kp, which is infinite. So if you put infinite here, 1 over infinite will be 0. Then again same step input, but you are applying to a type 2 system. Kp is infinite, so again as type 1, type 2 will also give 0 error for step input. To put it in another way, the step input will give an error of this much if there is type 0 system, an error of 0 if it is type 1 system, an error of 0 again if it is type 2 system. Then we take ramp input. The formula is 1 over kV. Now for type 0 system, a ramp input will have infinite error, and this ramp input, if you apply it to type 1 system, you have constant value, means a finite error. The ramp input applied to type 2 system will give you 0 error. Now parabolic input. Type 0 system will have infinite error, type 1 system will have infinite error, type 2 system will have finite constant error. You can see this table, all the diagonal terms, this diagonal, you have finite error. That means type 0 system will have finite error with step input. Type 1 system will have finite error with ramp input. Type 2 system will have finite error with parabolic input. This is the way we have to interpret the system, this table. Now let's see some example here. So this example shows a system G of S. This is G of S, this box. It's a negative feedback system, negative unity feedback system. So the question says find the errors for inputs of 5 UT and 5 TUT to the system shown. The function u of t is a step input, unit step input. Now here we have to make sure about what is the input we are giving. Of course it's a step input, but it's not unit step, it is a step of value 5. This table here talks about input step, means it's unit step. We assume unit step input. But here we have step input but equal to 5. So this point we have to take care of. So this is the system given. If you see the system, there is one S here. So this S tells you that this is a type 1 system because there is S power 1. So it's a type 1 system. Now going back to this table, type 1 system, you are giving a step input, it should give you 0 error. Now let's come back here. So this is the formula for finding step input error, steady state error for step input. Here I am going to use 5 over 1 plus limit s tends to 0 g of s. Now if you put 0 here in this g of s, when we say g of s, this is what is called g of s. So in this g of s, if you put s equal to 0, here you have 0, so it means the whole thing gets infinite. So it is 5 over infinite, which is 0. Now this is what we said in the table before. We said if you have a step 1 type 1 system and you give a step input, you will get 0 error. This is from this table. The second case is 5TUT. But before I go to that, here you have to be clear about this 5. As I said before, if it is unit step, then you will write 1 over 1 plus this thing. But since we have 5 as the input, here is the 5, this is the input. So we have to put that 5 here. Anyway, you are going to get 0 here. The second input we discuss is ramp input. Again, you have a type 1 system. From this table, a type 1 system for a ramp input will give you finite error. Now that finite error is how much? Here you are going to apply this formula 5 over limit s tends to 0 s g of s. Since you are going to multiply this g of s with s, so this is g of s and you are multiplying this g of s with s here. That means you are going to multiply this like this. Now this s and this s here, they will get cancelled, and then for this product, if you apply s equal to 0 here, it's like saying here 0 plus 2, that is 2, here 6, so 2 times 6 times 100 over, here it is 3 times 4, so 12, 12 in the denominator, and here if you apply here, you will get 5 times 1 over 100, that is 1 over 20. Now what is the meaning of this 1 over 20? This 1 over 20 says that if you give 5 as input to the system, the output which you are going to get will be 5. This is the output if there is no error. Now you have 1 over 20 as the error. So 5 minus 1 over 20, this will be the output, the steady state output for this system. That is the meaning of this 5 minus 1 over 20. Whereas here, if you apply this to a step input, this 0 indicates that the output will be, the steady state output will be 5 minus 0, that is 5. This is how we should interpret these numbers.